In this video, we focus on evaluating the physical properties of carboxylic acids, carboxylate salts, and esters. We are going to look at how we would go about comparing the boiling points, melting points, and water solubilities across these three important functional groups, and also look at how we would compare these properties with other functional groups that we've covered previously, such as alcohols, ketones, alkanes, and others. Let's go ahead and get started. When we think about the three functional groups, let's go ahead and draw out each of these to evaluate their physical properties by comparing the types of intermolecular interactions that each of these undergo. Remember from earlier videos that intermolecular interactions are the attractive forces that molecules engage in with other molecules. So if you have a container of a single substance, such as a container with millions of molecules of a particular carboxylic acid, those molecules are engaging in intermolecular interactions with the other carboxylic acid molecules that are present in the container. If you have an issue of water solubility, then the intermolecular interactions that we're looking at are the intermolecular interactions between the substance and water that are present within the same container. As we evaluate intermolecular interactions, these attractive forces between different compounds, we can look at a few different types of intermolecular interactions that come into play. The very, very important one, most strong of the interactions that we've talked about so far, is H bonding, hydrogen bonding, where you have an OH or an NH group that causes the oxygen to be very negatively polarized, the hydrogen to be very positively polarized, and then those can interact strongly with other groups. An intermolecular interaction that we have not previously talked about are electrostatic interactions. Electrostatic interactions are interactions between ionic compounds, specifically between cations and anions. So I'm going to put for electrostatics plus and minus to remind us that electrostatic interactions are very strong, and those are referring to the attraction of positively charged cations for negatively charged anions. And also, those positively charged cations and anions are strongly attracted to atoms that have the opposite polarity. So for example, a positive formal charged atom, such as sodium Na+, would be strongly attracted to an oxygen atom, which has a negative polarization. We can also look at so-called dipole-dipole interactions, which are where we look at polar groups interacting with one another. And then finally, we have van der Waals, which I'll abbreviate as VDW, which is the attractive force amongst generally be associated with nonpolar groups. So for example, when we are dealing with alkanes, the longer the carbon chain, the stronger the van der Waal forces. That is the atomic attraction of nonpolarized atoms. And this is the weakest of these forces here. So now, taking a look at these forces in the context of the types of molecules that we looked at, I'm going to start with the carboxylate salt. So in a carboxylate salt, we had a metal, such as, we'll put in sodium here. It would not necessarily have to be sodium, we'll put sodium in there. Oxygen, carbonyl group, and then our R group here, representing a carbon chain or carbon ring. Now remember, when we are dealing with these, there's a large electronegativity difference between a sodium and an oxygen, and so as a result, that becomes an ionic bond between these two atoms, and hence positive charge on sodium, negative charge on oxygen in this carboxylic acid salt, or also known as a carboxylate salt. Salt because of the fact that there's a positive and negative charge there. Then I'll draw out an analogous carboxylic acid, like so, And I say an analogous carboxylic acid because we have to make the assumption here that this R group is similar between the two substances in order to be comparing apples to apples, because you have one with a really, really long carbon chain and one with a really short carbon chain. That would certainly impact the intermolecular interactions that are at play there. So this is our carboxylic acid. And going back to what I was just mentioning about comparing apples to apples, that the compounds have to be similar in the construction of the R group, what we're going to make as our assumption here is that these molecules have similar molecular weights, meaning a similar atomic composition. Because it's very different, then we're going to have some different forces coming into play here. And then finally, our ester. Our ester will have, rather than OH, it'll have OR prime, where R prime is a carbon or more than one carbon, either or. Could be as little as a methyl group, could be a long carbon chain or giant carbon ring. And then R over here is the carbon chain extending off on that side. So this is our ester. And as we think about these substances in terms of their water solubility, this carboxylate salt is going to be the most soluble. And of the lineup here, the ester is going to be the least soluble of the group. The reason why carboxylate salts are the most soluble of this lineup is due to the fact that they have that salt quality. So that allows them to strongly engage in intermolecular interactions with water, increasing the solubility relative to a carboxylic acid. So in other words, you could think of the carboxylate salt as an example of extreme polarization, because it's not just polarized to the point of the two atoms having strong polarity, but instead the electrons have been totally transferred from one atom to the other, creating a salt, hence making the carboxylate salt much more water soluble than the corresponding carboxylic acid. When I say corresponding carboxylic acid, I'm referring to the carboxylic acid that has a similar molecular weight. And so this has important implications in terms of the applications of these molecules and the way that they interact with biological systems. Since a carboxylic acid is less water soluble than a carboxylate salt, by removing a proton from a carboxylic acid, which in the next video we will learn we can do by raising the pH of the system to create conditions that are somewhat basic to facilitate the removal of that proton from the acid through an acid-base reaction, we can create a carboxylate salt product that is considerably more water soluble. That is important when we consider things such as the food preservative sodium benzoate, which is a carboxylate salt, and why that would be more suitable to add to sodas and other foods because of its increased solubility over the corresponding carboxylic acid. At the other end of this spectrum of our functional groups that we focused on in this chapter, we have esters being the least soluble. And esters are the least soluble because they can't hydrogen bond with one another. They can somewhat engage in hydrogen bonds with water because of the fact that they have lone pair electrons on these oxygen atoms here. But they can act as a hydrogen bond acceptor. They can't act as a hydrogen bond donor, unlike carboxylic acids presented to this OH group, and then, as an extreme example, the carboxylate salts with the full negative and positive charges. So it's going to make esters less water soluble than these other functional groups. Esters in the water solubility realm will be more water soluble than aldehydes and ketones, and more water soluble than alkanes, alkenes, and alkynes. So if we wanted to extend this further down the line here, we could put aldehydes and ketones, and then much further down the line, we could put alkanes, alkenes, and alkynes. And this is, again, assuming that the carbon chain size and the molecular weight is similar amongst these compounds. If we were to compare esters to alcohols, we would find that alcohols would reside somewhere in the middle here between esters and carboxylic acids. And that is because in an alcohol molecule, we have a hydroxy group that is capable of hydrogen bond donation and acceptance, much like a carboxylic acid. And unlike an ester, where that hydroxy group that's capable of hydrogen bond accepting and donating is missing. But in the case of an alcohol, what's going to make that less water soluble than a carboxylic acid of a similar molecular weight is that the alcohol is lacking this carbonyl group, and that carbonyl group confers extra polarity onto the molecule, and also it allows hydrogen bond acceptance from this oxygen atom here. And so this is going to be our general lineup when we're assuming that the molecules have a similar molecular weight. If the molecules don't have a similar molecular weight, and that dissimilar molecular weight is due to an alkyl chain being longer in one molecule than the other, the presence of an alkyl chain will lower the solubility. So if you're dealing with two molecules and one of those has a longer alkyl chain than the other, that alkyl chain is going to serve to reduce the water solubility, making the molecule less water soluble. Now, as we look instead at boiling point and melting point, which I'll abbreviate as BP and MP here, when looking at boiling point and melting point, if we're comparing molecules that have a similar molecular weight as our prerequisite here, carboxylate salts are going to be the ones of the lineup here that have the highest melting point and boiling point. Carboxylic acids are going to be next, followed by alcohols, followed by esters, followed by aldehydes and ketones, alkenes, and alkanes. And you do have to consider here as well that this is, again, assuming a similar molecular weight. In the case of boiling point and melting point, if the carbon chain length increases, the van der Waals attractive forces amongst those structures with others of the same structure will increase, and that will lead to an increased boiling point and melting point amongst those compounds. And that's generally if you're comparing within similar functional groups and you have one of them with a longer carbon chain and one with a shorter carbon chain. The one with the longer carbon chain is going to be the one with the higher boiling point and melting point. But that longer carbon chain, in terms of water solubility, isn't going to play the same role if the carbon chain length increases. Increasing the van der Waals forces is not going to increase the water solubility because water doesn't participate strongly in van der Waals interactions. And so if the carbon chain length increases, the water solubility generally decreases, assuming that other features of the molecule are analogous, such as the functional group that are present. So when we're thinking about intermolecular interactions and we're thinking about how these molecules behave, we have to keep in mind not only the functional group, but also the molecular weight. And if the molecular weight is similar, then we're comparing apples to apples, and we can simply look at the functional group as our main driver of water solubility and boiling point and melting point. On the other hand, in the event that the carbon chain length is different, we have to think about what the factors and roles are of the increased carbon chain length, where increased carbon chain length increases the boiling point and melting point because it increases the attraction of molecules for other identical molecules that are present there in the container. But in terms of water solubility, increased van der Waals forces from carbon chains are going to make the molecule overall less polar, and it's going to make the molecule less similar to water, and hence decrease the water solubility.